All right, y'all. So today we're talking about more with rational functions, but in particular, we're going to be talking about graphing rational functions. In addition, we're going to also talk about solving equations which involve rational expressions. So it's kind of like if I have an equation which involves various rational functions, how do I solve it? So to start things off, I wanted to show y'all these notes I've put together. I put together these notes about rational functions. I'm hoping that you guys can go ahead and really utilize these notes to help you remember different things such as solving for X-intercepts, Y-intercepts, discontinuities, how to identify differences between vertical asymptotes and holes, as well as how end behavior works. My intention with these notes is that I know that it's very helpful for a lot of y'all to have sort of created your own notes, but for some people, they like to see the notes that I would make. So this is kind of my compilation of thoughts. And I'm going to be referring to these notes throughout this video. So to get started, let's just do a quick recap about sort of solving for features of rational functions. And I'm going to do this pretty quick because we've done it before. So the four features we said were X-intercepts, Y-intercepts, discontinuities, and end behavior. X-intercepts are the values of X such that the function equals 0. So for example, guys, if I have a rational function, remember rational functions are just fractions of polynomials. So polynomial divided by another polynomial. I can find the X-intercepts by basically just setting the numerator equal to 0. This is a very essential part of this. I'm going to actually bold that. So X-intercepts are always just the numerator equal to 0. So whatever makes this top part 0. Y-intercepts, it's the same for all functions. Every single function, all you do is just plug in 0 for X and evaluate it. Discontinuities are caused by division by 0. And so as a result, guys, essentially you can always solve for discontinuities by setting the denominator equal to 0. Right? That's the way that you always solve for your discontinuities. Now going a little bit deeper from that, right? Just because I set the denominator equal to 0 doesn't mean that I've actually figured out whether or not I have asymptotes, vertical asymptotes, or holes. So to go a little bit deeper, let's say that you solve for the zeros of your denominator, right? And what we can do is this. We assume that all those zeros are, first of all, vertical asymptotes. All right, so I have a vertical asymptote wherever the denominator equals 0. However, holes are caused by these discontinuities being removable. This is what we call it, a removable discontinuity. Essentially, a removable discontinuity means that the factor which caused the discontinuity, right? That factor in the denominator, it was able to cancel out with some factor in the numerator. So if you see this example here that I've got, I'll make it bigger. You see this example here? F of x equals x squared minus 1 over x minus 1. We see that the denominator would equal 0 when x equals positive 1, right? So I know that I have a discontinuity at x equals 1. But if I factor out the numerator, I can see that x minus 1 would cancel out, right? You see how it'll cancel out? Because it's canceling out, that means that the discontinuity at x equals 1 is not actually a vertical asymptote. It is a hole, which you can see kind of depicted in this picture right here. I'd recommend pulling up these notes yourself while you're looking at this video. So essentially the difference between a vertical asymptote and a hole is that in a vertical asymptote, that denominator would not cancel out, whereas in a hole, the denominator would cancel out like we got here. And then my function is just x plus 1. And then finally, end behavior, y'all. A little quick recap about end behavior. End behavior is essentially just an observation of the behavior, the growth, or any stagnation, right? Like flattening of a function as the x inputs grow towards negative infinity or infinity. That's basically meaning as x goes to negative infinity is just as I go to the left. As x goes to positive infinity is just as I go to the right. So it's like, what's the function doing as I go to the left and the right? In this function here, you can see as it goes to the right, it's flattening towards this horizontal asymptote. Okay, you can see that this is a horizontal asymptote at 4/3, and so this function that's depicted in this picture here has an end behavior of 4/3, and that has its own impact. We'll talk more about end behavior in a little bit. All right, y'all. So let's go ahead and do an example of graphing a rational function using these notes that we just talked about. Now, here I have a pretty complicated rational function. I was actually asked by someone to try to use a little bit more challenging examples in my videos because I think that they found that the challenge of the homework was harder than the challenge that I provided in my examples. So here I have one that I think is probably pretty hard to work with. So let's go ahead and get started. Now, before we talked about how like X-Intercept and discontinuities were solved by the zeros of the numerator and the denominator respectively. Because of that, I think it's really helpful to just right away when you're working with a rational function and trying to understand its features and how it works, just go ahead and factor the top and bottom as much as you can, because knowing those factors will be helpful for us in the future, in terms of like figuring out the discontinuities and the X-intercepts and all sorts of stuff. So let's go ahead and factor this out. So the denominator is going to be pretty easy to factor. The denominator is x squared minus 3x minus 4. That'd be, let's see, an x times an x to make x squared. Minus 4 and minus 3 is going to be made by minus 4 and plus 1. So I've got x minus 4 and x plus 1 on the bottom. Now the top part here, that's a little bit harder. That's fine though. What we can do is use rational zeros theorem, which we've talked about before. So the idea of rational zeros theorem is that I'm gonna, set the factors of the constant at the end of the function. So the factors of 8 over the factors of the leading coefficient, which is 3. Now, you can't tell me this ain't a hard problem out here, man. Come on. So the factors of 8 are 1, 2, 4, and 8. The factors of 3 are 1 and 3. And it could be plus or minus, right? This gives me a list of things to try out. And so what I'm going to do is I'm going to create a little table where I will try out my values. So here I have x, and my terms are 3x cubed, x squared, minus 10x, minus 8, and we'll see what they add up to when I plug in these different values of x. I like to personally start out with the ones just because I think that they're the easiest to plug in. So 1 over 1 would make positive 1, so I'm going to try out positive 1. Let's see what happens when I plug in positive 1. That would make 3 here, 1, minus 10, minus 8. Is that going to be 0? No, it's not going to be 0. So I'm going to I don't even care what this actually adds up to, right? I just know that it doesn't make 0. And all I care about, right, is finding zeros of this top function. Okay, let's try out negative 1, because I know that it could be plus or minus, right? Negative 1 cubed is still negative 1, times 3 is negative 3. Negative 1 squared is positive 1. Negative 1 times negative 10 is positive 10, and negative 8 is still going to be negative 8. What will this make? Oh, what do you know, dude? Look at this, look at this, look at this. Negative 3 plus 1 is negative 2, plus 10 is 8, minus 8 is 0. So I know that x equals negative 1 is one of my, that's one of my solutions here. So that means that if x is negative 1, then it must be that the factor was x plus 1. Uh-oh. We'll see that in the future. So then what I'm going to do, right, remember to factor a higher degree polynomial, I'm going to divide out the x plus 1 from this polynomial here. So x plus 1 divides 3x squared plus x squared minus 10x minus 8. I'm going to do this real quick because I think you guys are pretty good at this by now. I'd want 3x. Oh, that's 3x cubed, by the way, not squared. But I'd want 3x squared because that times x is 3x cubed plus 3x squared. Subtract this. Makes minus 2x squared. So I need to do minus 2x Subtract that. Negative 10 plus 2x would be minus 8x. And so I need minus 8. Cool. So I know that the factors at the top would be x plus 1 and 3x squared minus 2x minus 8. But I'm just going to go ahead and factor this right now because I can. So I want to factor 3x squared minus 2x minus 8. That'd make 3x an x, right? Because 3x times x makes 3x squared. And then how can I combine this to make it so that it multiplies to negative 8 and adds to negative 2? I think it's going to be like... Oh, yeah, it'd be like plus 4 and minus 2. Because like minus 2 times 3 is negative 6. 4 is 4. Negative 6 plus 4 is negative 2. Cool. So these are the factors at the top and these are the factors at the bottom. All right, so honestly, none of what I did so far was anything actually new. However, it is a little bit challenging to factor higher degree polynomials. But it's worth the work because now everything else should be actually really easy to do. Okay, so here's what I'm going to do, guys. What are all my x-intercepts? Earlier in the notes, I labeled intercepts as blue, so I'm gonna maintain that. My x-intercepts are negative 1. It's just whenever the top part equals 0, right? It's the zeros of the numerator. That'd be negative 4/3 and 2. Okay. How about the y-intercept? How do I solve for y-intercept? It's when you plug in 0 for x. If I plug in 0 for x here, the top part would just be negative 8. The bottom part would be negative 4. What's negative 8 divided negative 4? 2. All right, let's talk discontinuity. Discontinuity is when the denominator equals 0, right? So that'd be at 4 and negative 1. And we'll talk more about what's going on with that. The fact that there's a negative 1 discontinuity and an x-intercept at negative 1. The fact that these guys cancel out. We'll talk more about that in a sec. Finally, the end behavior. If you guys remember, end behavior is the, I'm going to do this in green. It's the leading terms divided, right? So it's going to be 3x cubed over x squared. If I divide that, that's equal to 3x. So that's my end behavior, 3x. Essentially, the function is going to follow the pattern that 3x does, which is going to be kind of like going upward on the right and downward on the left. All right, so let's start looking at this a little bit deeper, right? Now, the next thing to think about here, notice that my factor of x plus 1 on the top can cancel with the x plus 1 on the bottom. Do you guys see that? When this happens, when this can be done, that creates something. I'm gonna just write out, actually here, we'll write that later. So when a factor on the top and the bottom cancel out, it means that you have some x-intercept, which is the same as your discontinuity. In that case, when this happens, it means that that discontinuity was a whole. Remember, because it was a removable discontinuity. See how it's been removed? So like, what's my resultant? It's 3x plus 4 times, I gotta move my slide over, times x minus 2 all over x minus 4. So see how it has been removed? So we removed the discontinuity. Which creates the whole. All right, so negative 1 is a whole. All right, so I'm gonna actually, on my graph, I'm just gonna mark where negative 1 is so that I can keep in mind that there is a whole there. Okay. What about this 4 though? If the x minus 4 does not cancel out, then that is an asymptote. So I know that there's an asymptote at x equals 4. So marking this on my graph, here's x equals 4. And what I'm going to do is I'm going to do a dashed line. However, I'm going to do it in red because I want to keep, I'm also going to, actually, yeah, we should keep our color coordination. Let's do that. So over here, this hole, I'm going to mark with a red tick. I'm going to mark with a red tick because I know that there's a hole there. And the asymptote, I'm going to mark with a red dashed vertical line because it's a vertical asymptote. So remember guys, whenever you divide Whenever you have division by 0, it creates a discontinuity. If it is a removable discontinuity, like this x plus 1 was, then it creates a hole. If it's a non-removable discontinuity, like it doesn't cancel out, it creates a vertical asymptote. And this vertical asymptote is at x equals 4, the 0 of it. That doesn't look very clean. 4. There we go. Okay, let's start plotting other things. What about our intercepts? We said there is not, because of the discontinuity that was removed, there actually is no longer an x-intercept at -1. But there's still one at -4/3 and 2. So here I'm going to mark it. Here's 2, and -4/3 would be around here. Alrighty. And finally, my end behavior was 3x. So I'm going to mark that with a dashed line. And really what I'm going to do, guys, it's f of x equals 3x. If you remember, that's just a linear function. It looks kind of like this, right? It's a slope of 3. It's a line with a slope of 3. All right. So how does that all look? In fact, actually, I don't really want that line. To be honest, I think that what's going to be more important is for me to just keep in mind, keep in mind that this implies that the graph should be looking like that. It should be going up on the right side and down on the left side. So I'm just going to keep that in mind. All right, so now let's start. Can we start graphing this line? Oh, we still need the y-intercept. The y-intercept was 2. All right, cool. So we've got all our intercepts. We have our discontinuities plotted. We kind of know the end behavior. So we're about ready to go. The one last thing to do, guys, I think it is very important to not only identify where your hole is on the x-axis, but also on the y-axis. If you guys remember, a hole should actually have an xy coordinate. Okay, because it is a specific coordinate that is missing. You may be asking, how do I find that y coordinate then? Well, we know the x coordinate, right? It's at -1. So what we're going to do is we're going to take -1 and plug it in to our function, right? Since we were able to cancel out the x plus 1s, plugging in -1 is now allowed because I don't have any division by 0 from it. So solving for that hole, that y coordinate, I plug -1 in, and let's see what we get. We get 3 times -1 is -3 plus 4. -1 minus 2 is -3. And -1 minus 4 is -5. This would make 1. Okay, so we got 1 times -3 divided -5. That is -3 over -5, which is positive 3/5. So I know that this hole is going to be at x equals -1, y -3/5. So what I'm going to do is I'm going to mark that with a hole. All right. And what I'd like you guys to be doing when you're marking up your graph, label these things. So here, this intercept was at -4/3. This y-intercept was at 2. This intercept was at 2. And this hole was at -1, comma, -3/5. Oh, not negative, positive. My bad. See how it was positive 3/5? So that looks a little bit better, huh? So that hole is at 1, comma, 3/5. All right, so now what we can do, guys, is we can actually just start drawing this. So I'm going to draw the line with the black. Whenever you're graphing a rational function, y'all, it's going to be beneficial to start at some coordinate that we know, or to find some coordinate where it has a y value that is not 0. The reason why I want a y value that's not 0 is because, like, for example, this y-intercept, I want it because it helps me know, like, where I am. Like, these x-intercepts, I know where it is, but I don't know if the line should be going up or if the line should be going down from that x-intercept, right? I don't really know that. Well, but I do know where this guy is, and I know that from it, I should go towards this x-intercept, huh? And from it, I should go towards this hole and towards this x-intercept, huh? Do you see what I'm doing? So because I know where this y coordinate is, I can actually know my positioning. And it helps me go because then I can see the pattern of growth. Here I cut through this x-intercept because it has a multiplicity of 1, and I'm going to the right. What happens at the right of it? A vertical asymptote. So I'm going to go down towards negative infinity. And on over here, I cut through this intercept, and what's it going to do? I know based on my end behavior that it's going to go down towards negative infinity as x goes towards negative infinity. Finally, on the right side of this vertical asymptote, it was going down on the left, so on the right it's coming up. It's coming from infinity. But what's the end behavior look like? It should be going up. So at some point it would have curved and gone this way. So here I've sketched what this function, this rational function, should look like. Now, I know it might be intimidating how it is a bit complicated to sketch rational functions. But the most important part about these rational functions and the sketching of graphs is that we're solving for the features. Essentially, graphing in a math class is a lot of graphing is intended to force us and kind of create situations for us to think a lot about these functions, how they grow, what they look like on the inside, right? Where are their intercepts and all these features. We care more about the features than the line that results, because these features are oftentimes the significant pieces, right? So what I think I'm going to do is I'm going to do one more example, and I'm going to go a little bit quicker with it. And then we'll talk about solving rational equations. All right, so here I have another example of a rational function, which we're going to find all the features for and graph. So just like last time, I'm going to start off by factoring the numerator and the denominator as much as I can. So in the numerator, I can see that each term has a factor of x. So I'll pull out that x. So I pull out x, and I'm left with 2x minus 5. In the denominator, I actually have x squared minus 9. That's a difference of squares. So if you remember, that can factor into x minus 9. I mean, not 9. The square root of 9, which is 3, and times x plus 3. So first off, let's check. Do I have any factors in common in the numerator and the denominator? Is there any removable discontinuity? No, there's not, right? So that's pretty sick for me, because that means that my x-intercepts are actually going to be my x-intercepts, and my discontinuities will be vertical asymptotes. So let's see what this looks like. I would have my x-intercepts. When does x equal 0? Fun fact, when x equals 0. When does 2x minus 5 equal 0? 5 halves, aka 2.5. The y-intercept. When I plug 0 in for x here, I should get 0 on top, negative 9 on the bottom. What's 0 divided negative 9? 0, right? The discontinuities, that's the zeros of the denominator. That would be at 3 and negative 3. And I know that they're both asymptotes, right? They're both asymptotes. And finally, the end behavior. Okay, so end behavior is the leading terms divided. So I take 2x squared and I take x squared, and I want to divide them. So 2x squared divide x squared, that'd be 2. So I'm actually going to have an end behavior, which is y equals 2. Now let's look at how this all graphs together, right? How do I graph this all? Let's create an XY axis. Trying to be careful to make it clean. That's clean enough. That'll work. That'll do, pig. That'll do. All right, y'all. So let's plot out some stuff. So first of all, I was liking to use blue for my x-intercepts. So I have an x-intercept that's 0 and 5 halves. Here's 0. Remember, 5 halves would be 2.5. So here's 2.5. My y-intercept is at 0. Oh, what do you know? Fun fact, if you have an x-intercept at 0, then you also have a y-intercept at 0. Right? Because I don't need to explain that to you. My discontinuities, I have asymptotes at 3 and negative 3. So here's -3. I have an asymptote. That's a vertical asymptote. Notice that the equation of this vertical asymptote is x equals -3. If you have an equation which is x equals a number, then that's just a vertical asymptote, right? Because if x is -3, y can be anything, right? See, y is all numbers. So it makes like a vertical line. And x equals 3. And finally, I know that my end behavior should be 2. That is actually going to be at y equals 2, my end behavior. Because remember, guys, end behavior is talking about the function f of x, and f of x is the y-axis, right? Whereas x is the x-axis. So I have a horizontal asymptote. Notice, by the way, y'all, that if your end behavior is a number like 2, or even if it's 0, that makes a horizontal asymptote. If your end behavior is something like in the last example, it was x, it created a slanted asymptote. You know, the end behavior was a slant. Cool. So now we have all this stuff plotted, and we ask ourselves, well, how the hell do I draw this? Don't we? We say, Mr. Hobot, how do I draw this? That doesn't make any sense. Where's my coordinate that is above the x-axis? Where's my coordinate with a y value? I have none. Okay, so here's the thing. Sometimes, once you created all your features and drew it all out, your y-intercept is 0. This is the key here. My y-intercept is 0. So this is creating issues because I have nowhere to start. Because if you think about it, right, if I start at this point here, I don't know if I go up and down to this guy like that, or if I'm supposed to go down and up to it. I don't know which one I'm supposed to do. By the way, it's totally okay for this to cross that line there in the middle. This is the end behavior, right? So it only affects like the ends, not the middle. But so my point is I don't know whether this goes up or if it goes down. So how could I figure that out? The way I could do it is by just knowing where one of the coordinates is in between, right? Here's x equals 1. Let's just plug 1 in the function and see what we get out. So what would f of 1 equal? And this is one of those things, guys. If you're trying to make your graph more accurate, if you're trying to make a graph more accurate, it's actually very beneficial to create a little table of values so you can get out some coordinates and figure out what is my location at different points in time. So what about when x is 1? What is this? 1, so I get 1 squared is 1 times 2 is 2. 2 minus 5 over 1 minus 9 is -8. That's going to be -3 over -8, which is +3 over 8. So I know that at 1, I'm at 3/8, somewhere around here. Cool, so I know that my function should go from this intercept up to there and come on back down probably. Right? It should go from this intercept up to that point because I know that point is on the graph. And then here's another intercept, so I know I should come down to it. Going to the right of that intercept, I know that I'm hitting this asymptote, huh? So I'm going to go down. Why am I going down? It's because I was already going down, right? So I know that my graph isn't going to randomly change direction unless there was some reason. For example, if this was a multiplicity 2, 0, a 0 of multiplicity 2. But it's not, so it goes down. I can assume that it's coming up, but why not, find a coordinate so that we could know for sure if it's coming up. Here's 1, 2, 3, 4, x equals 4. When x equals 4, where am I? What's my y coordinate? Well, 4 squared is 16, times 2 is 32. 4 times 5 is -20, and 4 squared is 16 minus 9 is going to be 7. To be honest, I don't even need to know exactly what this value is. I just need to recognize that it's going to be positive because 32 minus 20 is 12. Divided by 7 is 12 over 7. the significant part here is that it's positive, so it must have been coming from above, right? So it must have been coming up like that. 12 over 7 is somewhere around here probably. So it must have like gone like this, and it goes towards my end behavior, which was y equals 2. Let's look to the left of this x-intercept. Well, as it was coming to the intercept, if I'm reading it to the left, it's going downward. So I'm going to keep going downward. And as you can imagine, we could probably have assumed that it's going to be coming from up, but you know, let's be sure about that. Let's plug in -4. -4 squared is positive 16 times 2 is positive 32. -4 times -5 is plus 20. -4 squared is 16 divided by, or minus 9 is going to be positive 7. That's a positive number. I'm not even going to bother. I just know that it's positive, so I know that it's above the x-axis, so it must have been coming from up. Do you guys see what I mean when I say that? I'm saying that essentially, because it's positive to the left of this, because I know that the function is positive at a value which is to the left of my asymptote, I know that it must have been coming from up, mostly because there's no x-intercept here, right? There's no x-intercept here. So it's like, if it was coming from down, I know I have this at x equals -4. I know I have some positive coordinate here. If it was coming down, coming from negative infinity, and it went up to that coordinate, notice that I have to cross the x-axis to do that. So I know that, but I know that there's no x-intercept here, so that must be impossible. So this is where I am. All right, y'all. So this was one more example, and this one was an example which had an end behavior of 2. So you saw that it made a horizontal asymptote. It had 2 vertical asymptotes, so it actually creates 2 asymptotes, which is kind of funky looking, huh? And it had a couple of intercepts, and we solved for some coordinates to know where it goes. So now what we're going to do is we're going to just wrap things up by talking a little bit about some strategies when you're solving rational equations which involve these rational functions. Alrighty, y'all. So here we are at the last bit of this video. Now, I know this is a new topic, but it is one that is actually a little bit of review from Algebra 2. And I just wanted to kind of talk a little bit of strategy. This is solving equations which have fractions where x values are in the denominator of those fractions. So these are rational expressions. Notice it's just like a rational function. It's like if I had 2 rational functions adding and they equal -1. So some strategies for solving these. The first step of solving any rational equation, the first thing to do is to remove the denominators. Just like with equations before, having a fraction is annoying, isn't it? Fractions suck. Let's be real. Fractions are terrible. So let's get rid of these denominators so that we don't have fractions anymore. When we're doing that, something that I highly recommend doing is first factor those denominators. We're going to factor the denominators because it will help us out with the part 2 of removing the denominators. So just for now, just accept that I'm going to factor this for good reasons. All right, so the bottom of this one is factored, or there's nothing to factor, but this guy, I could pull out x. I could pull out x and I'd be left with x minus 6. So I'm going to have x times x minus 6. Now, the reason why I wanted to factor the denominator is because then what I can do is I can determine. So then I can determine the least common multiple of the denominators. plural. Now, you may be saying, what does that mean? What is least common multiple? I'll show you guys an example. Y'all have actually done this before. It's like, what if I had the numbers 4 and 5? The least common multiple of 4 and 5 is 20. Why? Because 20 has factors 4 and 5. What about the least common multiple of 3 and 2? It'd be 6, because 6 has factors 3 and 2. Okay, you may be saying, okay, well, this is kind of lame, Mr. Hoba. Okay, but what if I had, what's the least common multiple of 4 and 8? It's 8. Why? Because 8's factors are 1, 2, 4, and 8. Notice that 4 is one of the factors of 8, and 8 is one of the factors of 8. So you can see it's called the least. It's called the least common multiple, because we're talking about, yes, 32 is a common multiple for 4 and 8, right? Because 4 times 8 is equal to 32. But I'm looking for the one that's the smallest number, which still has both of my numbers as its factors, as its potential factors. So another example would be something like, what if I had 6 and 9? The least common multiple of this would be 18, because the factors of 18 are 1, 2, 3, 6, 9, and 18. So 6 and 9 are contained. The easy way to find least common multiple between two numbers is to actually look at their factors. 6 is 2 times 3. 9 is 3 times 3. So I know that if I have a factor of 3, then I have it covered. Then I have both of these guys covered, right? If I have another 3, then I have that guy covered. And if I have a 2, I have that guy covered. 2 times 3 times 3 is 18. So what is this all to say? It's all to say that, notice, if I want to remove the denominators, I need to know kind of something that I can essentially multiply, some polynomial that I can multiply this equation by, such that it'll get rid of all these. But I don't want to be multiplying by too big of a polynomial, right? Because like, if I multiply by too big of a polynomial, I'm going to make this equation really complicated, right? Because whatever multiplies the left-hand side is also going to multiply the right-hand side. And so if I'm multiplying by some degree 3 polynomial, right, something with x cubed, then that's going to become annoying to solve the equation. So it's really just to make our life easier. So it's like, what's the least common multiple of x times x minus 6 and x minus 6? It's actually x times x minus 6. It's literally that. Because if I multiply this onto this term, it'll get rid of the denominator. If I multiply this onto this term, it'll get rid of the denominator and have a leftover x. And then it will also, because of solving equations, I have to do it to the other side as well. All right, so let's see what this looks like. So I'm going to actually take my equation here that I have created, and I'm going to bring it up a little bit, because there's no room to work. Oh my god. I have no room to work, huh? I dragged that dot up here. So we distribute, right? I multiply it through. I multiply it through. I multiply this guy through. What do I get? X times x minus 6, multiplying this term, the denominators will cancel, and I'm left with just minus 4, right? When I multiply it over here, I'd be left with 3x on the top, but I still have an x. Actually, you know what? Here, let me show the work. This is poor teaching by me to not show the work. I'll multiply x times x minus 6 to this, and I get negative 4 times x minus 6 all over x times x minus 6. I multiply it over here, and I get 3x times x minus 6 all over x minus 6. And that's equal to negative 1 times this. So negative x times x minus 6. All right, cool. Now let's look at what cancels out. The x's cancel. The x minus 6 cancel. X minus 6 cancels. So what does that leave me with? It leaves me with negative 4. 3x times x, so 3x squared. And it's equal to negative x times x minus 6. That's minus x squared plus 6x. You see how I've simplified it? And look at this. This is an equation which we can totally solve. It's a quadratic equation, y'all. So how do we solve a quadratic equation? You just get all your terms to one side equal to 0. So I want this equal to 0. So I'm gonna add x squared and minus 6x. So I end up with 3 plus 1 is 4x squared minus 6x minus 4. All right, how do I factor this guy? Well, every term has a multiple of 2. So I'm going to actually divide this all by 2. And I have 2x squared minus 3x minus 2 equals 0. And we got to factor this guy. So 2x, x, I need minus 2 to make minus 3. So I'm going to make this one be minus 2 and this one be plus 1. Because that multiplies negative 2, and 2 times negative 2 is negative 4, plus 1 is negative 3. And so what are my solutions? X equals negative 1/2 and 2. That's how you solve rational equations. One other thing, y'all. Once you have solved for your x values, I really strongly recommend looking at the original equation, taking them and looking at the original equation, and just double check, did I get any values here for my solution which cannot plug in? Because, you know, if, for example, if I got x equals 6, plugging this in, I would get 6 minus 6 is 0. Division by 0 is undefined. So if I were to accidentally get any X-Intercepts or any solutions for x such that I get division by 0, I should just go ahead and cross them off. So like, let's say that I did get, as one of my solutions, 6. What I would do is I would just look at it, say, oh, I can't have 6 because the x minus 6 on the bottom, and I would just cross it off. And so once again, my only solutions are negative 1/2 and 2. So that's a little bit about solving rational equations. Basically, just factor the denominator, figure out what you can multiply by that will cover all those factors, but without having too much extra, right? And multiply it out and then solve it like you would any equation. Solving rational equations is not too crazy, y'all. You got this. So, what we're going to do is go ahead and close out this video. You guys can check out the notes that I was talking about at the beginning in a link below in the description. I've also, and then for our homework, we will have 2 parts to it. There's going to be one part, which is a Delta Math assignment, and that's just to give us some practice, some rote practice with sort of solving for those features and graphing rational functions, and solving some practice with solving these rational equations. And then there's going to be a second part, which is a worksheet that I'm going to create. And that's just going to be so that I can create some specific problems that I want to see everyone solve. Just because Delta Math gives y'all, everyone gets individual problems or unique problems. So, hope you guys have a good day, and I'll see you all on Tuesday. Bye-bye.